everyone, and welcome to Picnic Day here at UC Davis in the Department of Chemistry. I'm Liz, a fifth-year graduate student in the department and the department's student outreach coordinator. Normally for Picnic Day, we have a bunch of shows filled with fun demonstrations and different hands-on activities. We're really sorry that you couldn't be here in person with us this year, but instead we're going to take advantage of the virtual format and give you an inside view to some of the research taking place in the Department of Chemistry. Plus, I promise there will be a fun bunch of demos mixed in. So, let's get started. As promised, we're going to show you a bunch of really great chemistry demonstrations. To help me out here is fourth year graduate student Croy and undergraduate Olivia. Thanks so much, friends.
This demo is going to be a great example of the different types of chemical energy, sort of like the fire in this propane tank. So this propane tank is going to initiate a combustion reaction that breaks down the propane into carbon dioxide and water, which is going to give this enough energy to break down some of the sugars in our gummy bear.
Yeah, and there are many different things that can act as an energy source for a combustion reaction aside from the sugar in this gummy bear, like any of the foods we eat, the nutrients, all of that.
So Olivia, what do you say? Do you torch this thing?
Oh yeah.
In this tube, I'm heating up solid potassium chloride to a molten liquid. This causes the solid salt to break down into potassium chloride and oxygen. The heat combined with the oxygen in this tube is going to break down the sugars in the gummy bear, so we can see how much energy there is in it.
Alright, and as promised, I'll now add this gummy bear into the molten mixture.
Hey guys. So, are you doing the garlic gummy bear demo?
Yeah,
Yeah.
we just finished up.
You know, this is actually my favorite demo, and it relates to my research.
How so?
So, in my research in the Gummy Lab, we also use sugar as an energy source.
That sounds super cool. I'd love to learn more about your research. Olivia and I have to clean up right now, but it might be a good idea to tag them along.
Welcome to the chemistry building.
Small microorganisms can do many things that I cannot do it. One, they can fix carbon dioxide, and they can convert carbon dioxide to useful chemical. And now technology is great, so we can modify microorganisms to produce chemical from carbon dioxide. What we are doing is a small step toward clean environment, but I hope our research can contribute to maintain clean environment for next generation.
Hello, welcome to my bench. This is the beautiful Gummy Lab. So should I talk to you guys about producing all sorts of different types of chemicals, specifically, green chemical energy. It's a little hard to show you biofuels and all sorts of stuff, so I have a really awesome visual demonstration for how we produce things in the Gummy Lab. So first off, we just have some normal E. coli. Now this is non-pathogenic, it's not going to hurt you, it's not like the different types of E. coli you hear about in the news. There's good E. coli and there's bad E. coli, just like there's good people and bad people. So as you can see, it's pretty yellow, kind of boring. So what I can do is I can introduce some DNA into it that expresses a red fluorescent protein. And voila, we get an E. coli culture that is now this sort of beautiful strawberry lemonade color. So the way that we do this is we have to build our DNA. But we still need something to read that DNA. And Tanner's actually going to give us a really awesome demonstration of how we put DNA into cells.
Hey everyone, so I'm Tanner, I'm a third year in the Gummy Lab, and whereas Morgan likes to work a lot with E. coli, I tend to work with cyanobacteria, which is this fun green photosynthetic organism that is super useful in green chemistry. So what I'm doing right now is I'm adding DNA to these bacteria to give them new instructions to make our molecule of interest. And so after this process is done, the cyanobacteria should be able to make bioplastic precursors, achieving our end goal of this project.
In the Atsumi Lab, we use a variety of sugars to feed our microbes. We have here our beautiful clean glucose, which we use initially to feed our strains to make biofuels or chemicals. But the goal of our lab is to be sustainable. So we want to use this crude agricultural waste extract to make biofuels and pharmaceuticals or any chemicals of interest, so we have a sustainable production system made in our lab. At the beginning of lab, we like to sit down, look at our notebook, and plan out our day. Our workflow usually consists of a bunch of PCR and cloning, which Tanner may have shown you a little bit of. We use our instruments in lab to quantify our chemicals being produced by our microbes, and we have to feed our bacteria every day so they can continue to grow and make the chemicals that we need.
Hi everyone, welcome to one of the teaching laboratory spaces here at UC Davis. This is a place where undergraduates will complete some of their coursework, or a place I get to test out some of my demos. Speaking of demos here, we have undergraduate Vivian Kellner here to help me out with this next demonstration. Now, as you'll notice, she's holding a very colorful solution, and whenever you're watching a movie and you see chemists, they're usually working with very colorful solutions. That's not always the case in our research. Sometimes it's clear, but in this case we added something a little extra special to monitor the reaction. So let's shake it up and see what happens.
Yeah, so the solution I have here is yellow, but if I give it a bit of a shake, it'll start to turn red. And if I shake it even more, then it goes green. And if we leave it still and I don't shake it anymore, then it should go back to red, and then eventually it'll be yellow again.
So what's special about this solution is it has a chemical called an indicator, and they're really useful for monitoring different types of reactions.
This specific indicator is called indigo carmine, and that's an oxygen sensitive indicator. So when I shake the flask and I get air in the solution, then I'm mixing oxygen in, and the indigo carmine will detect it. The reaction that's taking place is called an oxidation reaction, and you're probably familiar with this in your kitchen when you leave your bananas out for too long and they start to turn brown. The reverse of an oxidation reaction is a reduction reaction, and that's what's occurring when I stop shaking the flask and it turns back to red and then all the way back to yellow. Unfortunately, science has not yet found a way to perform a reduction reaction on your bananas and turn them from brown back to their nice yellow color.
That sure would be nice. Research of the future. Some chemical reactions change color, like the one we just saw.
Others give off gas, heat, light, or steam, like the one we're about to see. This graduated cylinder contains hydrogen peroxide, which is made up of hydrogen and oxygen.
Over time, it can break down into oxygen gas and water. Now, we can speed it up if we add a lot of energy like heat, or we can use something called a catalyst, like Vivian has here, and let's add it and see what happens.
Catalysts, like the one we just used to break down hydrogen peroxide, are very important in chemistry because they help us to make chemical reactions happen quickly and efficiently without having to put in a whole ton of energy.
Let's go see what our friends in the Shaw Lab are up to. I know they use catalysts and color-changing indicators in many of their reactions to make a wide variety of molecules.
My research focuses on finding ways to make organic molecules. These are molecules that either occur in the natural world or have an impact on biological systems. And as such, these molecules can be used as starting points for the discovery of new medicines. What I love about organic chemistry is it gives you the opportunity to build things. And just like working with any other material, you can build something and see what it does. Even though the things we build are microscopic, the ability to put them together and see how they operate is really fun and exciting. I see my lab's research changing the world in two ways. Because we find new organic molecules, we potentially find new leads for new medicines. And the second way in which my lab might change the world is that I get to work with extremely talented students, and my hope is that I can inspire them to go on and start their own labs and also enable their own new discoveries.
Hi everyone, my name's Sarah. I'm a third year here in the Shaw Lab, and the Shaw Lab is an organic chemistry lab. So basically what we do is that we make new reactions and then find ways to apply that to make new molecules. I joined the Shaw Lab because I really wanted to be an organic chemist. And growing up, I always thought it was really fascinating how medicines worked and that they were made of these small molecules. And so when I went to grad school, I wanted to be able to make those molecules and then one day be able to contribute maybe to making a new pharmaceutical or drug of some sort. What excites me most about my research is that I really love working with my hands, and the ability to make new molecules and things that have never been invented before is really cool to me. But in reality, one of my favorite things is the group of people I work with. They're a really fun bunch, we have a really great time together, and it's just a really overall positive atmosphere to work in. So today I'm going to show you guys actually one of our favorite reactions in the Shaw Lab. So this is a molecule that is in an oxidized form, and that's why it's bright pink. So really highly oxidized things can be really colorful. And so this is an indication that it's oxidized and we did something right. And then we're going to take our catalyst that we have, and as soon as we throw our catalyst in there, it's actually going to reduce the molecule, and it's going to bubble nitrogen off, and then it's going to go from pink to clear. And that's going to indicate that our reaction is complete once we see a full color change.
Welcome back everyone. We're going to do another demonstration that shows a different type of chemical reaction that can produce a color change.
So in front of us we have 3 crucibles, each containing this white powder, but they each have a unique metal salt in them.
These are the same metals that are ignited inside of fireworks to produce all the brilliant colors that we see on the 4th of July.
But instead of using fire, we're going to use some concentrated sulfuric acid.
So as we saw in the last demonstration, those metals can produce brilliant colors, like when we ignited the potassium, the sodium, and the strontium. This time we're going to use magnesium. Now what's special about magnesium is that it can burn at a very, very high temperature.
So what we have here is some magnesium metal in the form of a coil, and when we place this on a block of dry ice, and when Liz adds a little bit of solid magnesium metal, we're going to light this in the block of dry ice, and that's going to generate a reaction that creates a really brilliant white light. And the metal's going to burn so intensely that it's going to take oxygen from the carbon dioxide to form this black soot at the end of the reaction. So let's see what happens when we light this thing.
As you can see, metals can do some pretty incredible things, but they do more than just make pretty colors. Let's go over to the Velasquez Lab and see how they use metals in their chemistry to solve problems related to energy and the environment.
Our research program here at UC Davis is dedicated on the design of electrocatalysts and materials for water remediation. These materials are inorganic solids that are comprised of different combinations of transition metals. When you combine them in a certain arrangement, you create ranges of different types of compounds that perhaps could give us functionality to control reactivity on really important reactions. Reactions such as perhaps harvesting the energy of the sun, reducing CO2 to water to produce fuel on demand. We could further manipulate these compounds in ways like a Rubik's cubes, so we could arrange them in networks of pores and remove contaminants from water upon demand.
Welcome to the Velasquez Lab. My name is Jessica Ortiz. I'm a third-year graduate student here, and I'm going to show you a little bit of what I do. So this is the glove box. This is where we prepare our setup that we're going to put in that conventional microwave. So just as an example, this is a typical setup in which we have our metallic precursors pressed into pellets right here. They're inside a quartz tube that is filled with an insulating material, which is aluminum wool. So we're gonna take one of this to the microwave, and you're gonna see how the synthesis process goes. So this is the setup that we picked from the glove box. Now we're gonna insert it into this aluminum wool insulation material that has graphite on to get it to a very high temperature. So I'm just gonna insert it here, take off the paraffin, and then now I can put it in my conventional microwave. After doing the setup, doing the microwave synthesis, we check our catalyst, we characterize it more, and once we know what we have, we bring it here to the electrochemical station. So here we test how good this catalyst is gonna be by passing some electricity to it. And in this case, I have a platinum wire connected here, so it's producing hydrogen, so you're gonna see some bubbles being emitted from the catalyst. Ideally, we will have CO2 reduction, and then we will turn this into products of Ichthyrus such as methanol, methane, CO, and other materials that we can use.
One of many points of inspiration for the design of this research program at UC Davis dates back when I was a kid in Puerto Rico. Puerto Rico is an island that is located in the Caribbean and is highly susceptible to hurricanes. Once a hurricane hits, infrastructure like the electrical grid gets damaged, and access to clean water becomes extremely difficult. If you come from low-income communities like I did, access to water and energy becomes a commodity. The necessity that I experienced throughout those years basically allowed me to figure out a way for me to contemplate a program that will try to solve those problems for such communities.
For my research, I use transition metal oxides to design filters that can be implemented at various sanitation facilities. So one of the facilities is where we clean the water that we have in our taps that we use for drinking, cooking, cleaning, and there's also a lot of water that comes from composting facilities. So every time you get food, for example, and you throw away that compostable plate or that compostable cup, once it goes to the composting facility, it can degrade, produce a lot of toxic contaminants, so we can use those metal oxides to remove those from water as well.
We hope you've enjoyed this behind-the-scenes look at the chemistry department and some of the great research we've got going on.
We're sending this picnic day out with a bang, and we look forward to seeing you next year in April of 2022.
And in the meantime, if you want to get in touch with us, you can email us at chem-outreach@ucdavis.edu to learn more about some of the outreach activities that we offer to the community.
We're happy to set up lab tours or demonstrations. Plus, we have tons of great content on the department's YouTube and Instagram pages.
So thanks again for watching, and we hope to see you next year.